Okay, so in this video I wanted to real quickly discuss the application problems for our integration questions that we'll see on the test tomorrow. This will give us a heads up before we chat about this in person. On number 13 of our practice exam in Math Excel, we're told that a force of 60 newtons is required to stretch and hold a spring 0.1 meters from its equilibrium position. So just to be clear here, if I've got, I'm going to draw this horizontally here so we don't have gravity at play. If I've got a spring attached to a wall, if I don't have any pressure on that spring, this position is what we would call its equilibrium position, wherever this is in terms of x, if x represents the distance from the wall. Now I could push in on that spring or I could pull out on that spring, and it always wants to return back to its equilibrium or rest position. Now, if the spring obeys Hooke's law as it's described here in part A, then we can find what's called the spring constant. Springs that obey Hooke's law have a constant value to them in a unit called a Newton per meter. And that's necessary because Hooke's law states that the force necessary to maintain a spring with a particular constant at a particular distance from its equilibrium is force equals K times X. So in this particular case here, if 60 newtons of force is necessary to stretch a spring 0.1 meters away, well, if force is equal to K times X, and we know that K would be the result of the force divided by X, we know that 60 newtons of force divided by 0.1 meters ends up being 600, and the units do produce a Newton per meter unit. So we can report 600 as our K value here. Now where calculus comes into play is this. If I'm pushing this spring and I continue to compress it, well, we need a certain amount of force to compress and hold the spring here. We need a different force here and here and here and here. That force quantity keeps changing as we move to a different position, as we collapse this spring. And similarly, if we were to expand or extend the spring. And at each of those positions, we could sum together the amount of force necessary to accomplish that task. So since we have an infinite amount of sums, then we can set up an integral to accomplish this. In our physics class, which is algebra-based, we'll just use an average force quantity, and we won't have to worry about these infinite sums. But for us, since we can handle the precise and exact force quantities at each position, then the integral will suffice. So the setup is going to look something like this. I'm going to write it down here off to the side. If we sum together all of the forces where we have K times X from some starting position A and some ending position B, we can integrate this equation with respect to X. So in our case, for this particular problem, we're compressing from 0.3 meters from its equilibrium position, and that's it. So we could integrate from 0 to 0.3. Our K value was 600 X, and we'll integrate with respect to X. So there's our setup. We can let the calculator do the work for us, or we can integrate this by hand. Either one is perfectly fine, and we can obtain our result. And it looks like our result from our calculator comes out to be 27. I did that one off screen. And the unit for this is joules. We'll talk more about this in physics class, but if our unit for the K value is a Newton per meter, and we multiply it by a distance, horizontal distance, which is a meter, you might think that those two units will cancel down to newtons, but let's not forget that the sum of our infinite number of differentials, those two together, also represent a horizontal distance, which is going to be a meter. So the resulting unit ends up being, well, if this meter cancels with that meter, we end up with a Newton times a meter, which is also known as a joule when we measure work in physics class. So that's pretty much it. That's the process. In question C, we just have a slightly different setup. This time we're stretching it 0.5 meters from its equilibrium. So if we start at 0 and go to 0.5 of, let's see here, we had 600 times x with respect to x. Again, we could use the calculator, or we could integrate that by hand. It looks like that answer would be 75 joules, if we trust Math Excel's work. For the third example here, the last part of this particular problem, we've already stretched 0.1 meters from the equilibrium, and I think what they're trying to say here is that we're trying to stretch it another 0.1 meters. So in this case, the integral starts at 0.1, and we're going to have to stretch to 0.2 to obtain the additional stretch. So if we go from 0.1 to 0.2 of 600x with respect to x, then the solution to that integral should tell us the amount of additional work necessary to compress or stretch that spring. So I hope that helps, and hopefully that gives you something to think about and work on, and maybe you can come to class tomorrow with additional questions as needed. In our final example, I'll just reiterate how Math Excel suggests that we complete this problem, and I do like this technique, so I'm going to go ahead and repeat it as well. We've got the dam that's in front of us here. This is kind of the front view on an XY axis. If we center the dam on the XY axis, we can note that the width of the dam here is going to be necessary to help us compute the cross-sectional area. So we're going to do a little bit of work to compute that, but before we get too far, we'll just remind ourselves that the total amount of force that the dam is capable of holding, or that is holding back if it's filled with water, would be the integral from A to B of rho, the density of the fluid, times g, the gravitational acceleration experienced, times the height of the dam minus y, times the width of the dam relative to y, based on y. We're going to integrate with respect to y. So if we're integrating with respect to y, that means that this a value and b value here are actually height values, so from a up to b. And a lot of times we're considering, a dam filled with water all the way up to its brim. And so a lot of times we're just going to use an A value of 0 and a B value of the height of the dam. But if for some reason the water is not filled all the way up, or maybe there was some, something preventing the water from filling up all the way to the bottom of the dam, then we could modify that as needed. But the tricky part here is, I think, finding the width function in terms of y. Now, the width of the dam, we can imagine this linear equation right here representing the right side of the dam. And if we double the quantity that's measured here, then because of this symmetry on the left-hand side, doubling that right-hand quantity would allow us to compute the total width of the dam. So that's kind of the tricky part with one that's in this particular shape. And there are lots of different ways to find the equation that represents this line that's marking the edge of our dam. We can consider the two coordinates, 17, 0, and what would this next one be? Half of 68, what's that, 34, 0. And with those two coordinates, we can calculate slope. We can use the point slope formula to find our equation. But I think we actually luck out here. This isn't all that difficult. We have a rise of 51 meters and a run of 17, because to go from 17 rightward to 34 is 17. So this would be y equals 51/17 x plus our y-intercept. And conveniently, if our rise is 51 but our run is 17, if this is a distance of 17 horizontally and this is a distance of 17 horizontally, then I know I just have to drop down 51 units and I will intersect the y-axis down here. So we'll call this minus 51. Now that equation's good in terms of x. We've got y equals something in terms of x, but in reality, since we want our function based on y, we should rearrange this. So to isolate x, we would add 51 to both sides. And then we could divide by 51/7 or multiply by 17/51. Now, the x value given any y value can be computed with that equation, but let's recall that the width of the dam, based on our y coordinate, is going to be 2 times whatever x coordinate we get. So I'm just going to double this, and I'm going to call this 34/51 times y plus 51. Now that expression would give me the width of the dam, not just the position of the x or the y value. Okay, so moving on, let's just double check some things here. We have the dam that's got water all the way up to the top of the dam. We're going to use 9.8 as our acceleration due to gravity, 1,000 for our density of the water, and I think we can proceed from there. The function that I would enter into the calculator would then be the integral from 0 up to 51 along the y-axis, with 1,000 as our density and 9.8 as our gravitational acceleration. The height of the dam is 51, take away y. Remember, we're doing that because up here, when y is equal to, say, 51, there's almost no force associated with the water at that top of the level. And if we drop down a little bit, there's not a whole lot of water column producing pressure that we have to worry about. So 51 minus 50, for example, gives us a small quantity to compute our pressure against. So 51 minus our y coordinate, and our width based on y is that green equation that we just set up here, 34/51 times y plus 51. And we would integrate that with respect to y. So as far as a test question goes, this is the setup that I'm looking for, and of course we can let our calculator produce the result for us. For Math Excel, I haven't done the Math Excel set in a while, so they may have us kind of rearrange some equations a little bit. I don't know exactly what's happening here. I wonder if 34/51 reduces to 2/3. And I would guess that B is the answer, but I may have made a mistake too. I hope I didn't, but if I did, you all can bring that to me tomorrow in class. But the long and short of it is this: I'm not asking you to go through all these intermediate steps for the test tomorrow. I'm really just interested if you can learn the pattern and utilize this density formula to calculate the amount of force that the dam can withhold. So there's our setup. Make sure that you try these on your own and bring them to class tomorrow. We'll chat about them before we get the test started. Okay, thanks a lot for watching. See you tomorrow.